Share screen. Okay. Okay, so today's lecture is well, today's and the next lecture in the series are a slight aside from the main thrust of the lectures so far. You would recognize that what we're doing here is we're building up essentially perturbation theory in path integrals. And so I started by looking at a one-dimensional integral, and then we move on to quantum mechanics, and then we'll move on to quantum field theory, and then we'll add fermions to the problem, etc. The only thing we're not going to do is gauge theories, because that really will take a lot more time. I would love to teach a separate course in path integrals and gauge theory, but that's for another time. Today, and possibly for the next lecture, I want to talk about something slightly different. My goal here is to introduce the idea of statistics, particle statistics in path integrals. And this is because we'll come back to the idea of the difference between bosons and fermions a little later in the story. But I want to introduce it by bringing in the idea of topology into the path integral. So here, by topology, I mean the topology of the configuration space, the space in which the quantum particle lives in. So up until now, we've assumed that the space is trivial, meaning it's flat without any topologically interesting features. And by topologically interesting features, I mean like handles or holes that would convert this flat space into something like a torus or punctured torus or something like that. Okay, so we've assumed none of that holds in this case, and we're dealing with an essentially topologically trivial, and in fact just geometrically as well as topologically trivial configuration space. And there's certainly enormous amounts that we could talk about path integrals and curve space. There are books written on the topic, and indeed, if you want to try and apply path integration to gravity, then you certainly need to be able to talk about path integrals in curved space. But we don't want to do that today. So we're going to stick with flat space, and we're going to do the kind of simplest thing possible we can think of to make this topologically non-trivial. And the simplest thing we can think of is to just make a hole in it. So we're going to consider, instead of a plane, we want to consider a punctured plane. So one reason you might want to think about why you would puncture the plane and think about path integrals on this punctured plane is the following. Topologically speaking, and by which I mean you should think about the configuration space as some kind of rubber band, right? So I can deform it, I can stretch it, I can squash it, I can twist it, and as long as I don't do anything drastic to it, and by drastic here I mean something like cut it or puncture it, then I'm allowed to do these geometrical things to it. Now, topologically speaking, and again, by which I mean you should think about this space now as some kind of rubber band. So imagine I have a two-dimensional sheet of rubber, and I puncture this sheet, and I'm allowed to squash this thing and twist it and stretch it. So you grab a hold of the hole and you pull it apart. And you pull it apart right up until the boundary of the space. And you realize that topologically speaking, a particle moving on a punctured plane is essentially the same physics as a particle moving in a loop, in a circle. So a particle in a circle, topologically speaking, is the same as a particle moving on a punctured plane. So if you want to learn how to do integrals with particles in a circle, and one time you might want to consider doing this is when you want to consider a particle moving in, for example, a current loop, is by considering what happens if you make a single hole in the plane so that the particle moves on a punctured plane. Okay, so the question I would like to ask today is, how do we use path integrals to treat a particle moving on a two-dimensional plane with a hole in it. Using a path integral. Another reason you might want to consider doing this is because of something called the Aharonov-Bohm effect. The Aharonov-Bohm effect, firstly, Nitin, have you heard of the Aharonov-Bohm effect? I assume yes.
Yeah.
Okay. Have you studied it? Have you?
Yes, that is it.
Good. Okay. So the Aharonov-Bohm effect, as you would know, actually takes place on a punctured plane. In this case, the punctured plane is facilitated by the puncturing of the plane is facilitated by putting a solenoid in the plane. And the main point here is that the Aharonov-Bohm effect demonstrates the quantum nature of the interaction of a charged particle in an electromagnetic field. So let's consider, so we want to exhibit this non-trivial topology with the Aharonov-Bohm effect. So classically, we know that charged particles interact only with electric and magnetic fields, so the E and the B fields. And so while we can certainly express the electric and magnetic fields in terms of an electromagnetic potential, the electromagnetic potential itself doesn't appear to play a fundamental role in classical electrodynamics, meaning that you needn't say anything about a scalar potential or a vector potential in order to study observable phenomena in classical electrodynamics. This is no longer true quantum mechanically. So if I have a quantum particle interacting with even a classical electromagnetic field, then I can no longer just use the electromagnetic potential as a mathematical nicety. It turns out that there are physical consequences to there being an electromagnetic potential, right? And to see why, Aharonov and Bohm devised an interesting thought experiment. So I went to an interesting lecture by Aharonov in Princeton a couple of years ago, where he was talking about his philosophy in trying to understand these quantum phenomena. And he was saying that whenever he wants to learn something new, for example, the way he learns about it is to find somewhere where it doesn't work, something like a paradox, and expand on this paradox and try and understand where the theory you're trying to learn about fails. And I found this a very interesting point of view because, typically when we learn something new, like quantum theory or, general relativity or string theory, we tend to focus on what is known about the theory. And we look back on these ideas with hindsight. And hindsight, as they say, is always 20/20. Meaning, we tend to not learn about places where the theory fails. We tend to focus on all the good things about the theory. And I don't mean fail here in a negative sense. I mean fail as in a paradox, something that you can't explain using the current theory. And this is how you push these ideas in science, right? You find somewhere that is just a puzzle, and you try and solve the puzzle. And in the process, you learn where things, you learn the boundary of things. And this is what Hernan and Bohm did. They approached this problem, and the problem was a standard double slit experiment. So as you know, as every first year student in physics knows, if you take a beam of particles, pass it through the double slit, then there is quantum interference, which results in an interference pattern that's produced on a screen further downstream. Right. What Hernan and Bohm did was they said, well, what happens if we turn on a magnetic flux? And we'll turn on the magnetic flux in a region in which the charged particles are completely shielded from. Okay, so what they did was they said, well, let's consider the following. Let's consider the following physical system. I'm going to draw a picture now. So here I have a double slit. Okay, and I have a screen further down the line. The screen looks like that. So this is the screen. And this is the double slit. And I'm going to put a solenoid, which I'm going to denote like this. So this is a solenoid which is perpendicular to the plane, and in such a way that the magnetic field comes out perpendicular from the plane of the board. This is my solenoid, and I'm going to make sure that the solenoid is sufficiently long that I don't have to worry about any edge effects where the magnetic field curls back on itself, right? So if I make sure that it's sufficiently long, you know, think about it as an infinitely long solenoid, then I don't have to worry about the edge effects. In principle, these edge effects can be accounted for, but they add complication that I don't really care about in this treatment. So then what we want to do is we want to put a source of, let's say, a particle beam somewhere down here. All right, so this will be our source. And then we want to consider paths that start at this beam and take the one path, or start at this beam at the source and take the other path and end up at the screen. We'll call the one set of paths that pass through slit 1, x1 of t. And the second set that pass through slit 2, we'll call x2 of t. And the question is, how do we treat this using a path integral? Okay, so this is the Aharonov-Bohm effect. The fact that, so what Aharonov and Bohm reasoned was that if you turn on the solenoid, so if you pass a current through the solenoid so that it generates a magnetic field, the particles traveling along the paths, the blue paths, cannot experience any interaction with the magnetic field. The magnetic field is completely contained within the red region. Okay, so the particle itself doesn't interact with the magnetic field. Yet, what they've reasoned and what was found in experiments later on was that when you turn on the solenoid, there is a shift in the interference pattern on the screen. So here's the screen, and what you would see is an interference pattern, and the interference pattern would look something like this, say. So there would just be some interference pattern on the screen. So light and dark patches, which I'm going to denote by some set of waves like this. And what they found was you get a shift in this pattern when you turned on the magnetic field. When you turned on the magnetic, the solenoid, which generated magnetic flux through the plane. And so the question is, if a particle is not interacting with any magnetic field at all, how does it know that there is one present? Right? So nowhere in this particle's configuration space can it access the magnetic field, but we thought previously that particles only interact with the electric and magnetic fields and not with the electric and magnetic potential, or rather not with the scalar and vector potentials, because that's just a mathematical trick to code certain properties of the electric and magnetic fields. The fact that an electric field of a point source is radially directed and a magnetic field of a solenoid, the magnetic field of a line charge is like a curl. So it curls around the field. So, okay. So that's what you learned in first year. And now it seems like there's a puzzle. Why do you see it shift in the interference pattern on the screen if you turn on the magnetic field? So let's see how we would code. Yes, question.
Shouldn't we actually expect a shift? Because
why?
This source or the particle is supposedly quantum mechanical, so we can't really.
Why? Those are just words, right? Why should the particle that the interior of the solenoid is inaccessible to the particle?
Yes. So I was reading, I think, Anthony Z's book on quantum field theory once, and he said that Feynman thought of this either Feynman or Z himself thought of this path integral formalism as like, let's say you are basically you are counting all the possible paths instead of saying that there are no paths. You are sort of building through all the possible paths, right?
Sure.
So if we think in those terms, then of course the particle, if we even consider it as a particle, then when it goes through this either of the slits, then it would also interact with the region in which solenoid is located. No.
Okay, but the quantum particle doesn't. So the paths are not equally weighted. Do you agree?
Yes.
So I can build the fact that I have a solenoid in a region that is not accessible to the particle by putting the interior of a particle of that solenoid in something like an infinite square well.
Sorry, could you repeat that again?
So I want to. So imagine I have a region. I have a particle moving on a plane. Say I have a particle moving in a line.
Yeah.
Okay. And I want to make sure that that particle doesn't access a particular part of that line.
Okay.
So I can put that part of the line in a potential well.
Okay.
Now you're quite correct. The particle can tunnel into the potential well.
Yeah.
Okay. Which is what Z is saying in that statement. It's the fact that in a quantum system, you have to actually code the fact that quantum tunneling is possible.
Yes.
But quantum tunneling comes with a certain probability, which in the language of path integrals translates into the fact that the particle is weighted, the path integral is weighted by a factor of e to the is.
Yes, definitely.
Right. And so you remember that the weighting decreases the further away from the classical path I go.
Yes.
So the classical paths are the ones that cannot access the interior of the solenoid region.
Yeah.
So the paths, there are paths that go into the solenoid region.
Yes.
But those are infinitesimal relative to the paths that are outside. And so they don't actually contribute, or they contribute, a set of measure 0 paths to the path integral.
So we would still not expect them to have any effect on the interference pattern.
Correct. However, I'll show you how we think about how the effect actually arises now. That's the point of this lecture.
Okay, sure. Thank you.
Okay. So why should we expect an effect? Okay. So here we have to ask what happens before we turn on the magnetic field and what happens after we turn on the magnetic field. Before we turn on the magnetic field, the action for the particle evaluated on each path is S evaluated on x1 and S evaluated at x2. Do you agree?
Yes.
Okay. Now, the interference, which is really all we care about, because that's what's contributing to the interference pattern on the screen. The interference of the amplitudes between the two paths is computed by the sum of the two weighting factors. So e to the I s1 or e to the I s at x1 plus e to the I s at x2 of t. So let's pull out a factor of e to the I s at x1. I'm going to leave out the t dependence there because it's clear what we're talking about. And that gives me a 1 plus e to the I s at x2 minus s at x1. Both of these are vectors. Okay, in units of h pi equals 1. This quantity, the difference in the two actions, on-shell actions, that is, I evaluated on a particular path, is what's called the relative phase between the two paths. Let's call this phi12. So this is the relative phase between the two paths, and it is what controls the interference pattern. Okay. Okay. In particular, if phi12 is some integer multiple of 2 pi, then the paths interfere constructively. And if phi12 is an odd multiple, sorry, is an even multiple sorry, what am I saying? If phi12 is an even multiple of pi, then the paths interfere constructively and they interfere destructively if phi12 is an odd multiple of pi. Right? And some general combination of the two, if not. So in particular, if phi12 is an even multiple of pi, so 2k pi, the paths interfere constructively and destructively if phi12 is an odd multiple, so 2k plus 1 times pi. Okay, and this is before we turn on any magnetic flux. So now suppose we go back to our experiment and we turn on the solenoid. So we generate a magnetic field perpendicular to the plane. In other words, we give a non-vanishing flux through that plane. If we turn on the flux, then the following happens. So turning on a magnetic field which I'm going to call B, and B is going to be the curl of a vector potential, A, has the following effect on the dynamics of the particle. The Lagrangian of the particle changes from L, the original Lagrangian, to the following. From L, which is a function of x and x dot, to, let's call it L tilde, which is also a function of x, x dot, but now also of the vector potential. And this guy is L minus the charge of the particle times its velocity dotted into the vector potential. Okay. And as a calculation, I'd like you guys to check that this produces the correct Lorentz force law. Okay, for a particle moving in an electromagnetic field. So how does this affect the action? The action, recall, is the integral of the Lagrangian over time. So with this, the action changes as well, and the action changes by the following amount. The amount is minus q times the integral over time of this v dot a part. But v is, of course, dx by dt dotted into a, which tells me that this is nothing but an integral over line integral dx dot a over some path gamma taken by the particle. So this is the path taken by the particle. Okay, right. So that's how much the action changes by. So in other words, with a magnetic field present, the action changes by the following. So in the presence of a magnetic field, the action S to the function of the paths xi of t goes to S, let's call it tilde of xi of t, which is S of xi of t minus q times the integral over gamma I, where gamma I is either gamma 1 for x1 parts or gamma 2 for x2 parts, dx dot a. Okay. As in the case of the no magnetic field present, I can calculate the interference by looking at how the different amplitudes sum up. So I add e to the I s at x1 plus e to the I s at x2. And so the interference is given by a similar factor of e to the I s at x1. Sorry, this is s tilde at x1 multiplied by 1 plus e to the I phi tilde 1, 2, right? Where now this phi tilde 1, 2 is the important bit. So this guy, phi tilde 1, 2, is equal to phi 1, 2 the original relative phase minus q times an integral over the path gamma 2 dx dot a minus an integral over the paths x1 dx dot a. And I can turn the difference of these two paths, if you go back and look at our picture, the paths x1 and the paths x2 with a minus sign tell me that I have to take a closed loop around the whole blue set of paths. And if I do that, then I can rewrite this guy as phi 1, 2 minus q times a closed integral of dx dot a, and the closed integral of dx dot a is nothing but the flux, what we call the magnetic flux through the plane. So this is just phi 1, 2, the original relative phase, minus q times the magnetic flux through the plane. Okay, so this is a magnetic flux contained inside the closed loop bounded by the two paths. Great. Okay, so that tells us what the interference is. Now let's calculate some actual amplitudes, which involves taking path integrals over the paths of the e to the is weightings. So if I'm going to call the amplitude of the magnetic field turned off AI. So with no magnetic field, the amplitude is AI, and I'm going to define AI to be the path integral over paths x of e to the is evaluated on x, and I take these integrals over paths gamma i. Right? When I turn the path, when I turn magnetic field on, so with magnetic field turned on, the AI amplitudes become AI tilde, say, and the AI tilde is given by the same path integral over paths x taken over gamma I, e to the, in fact, let's write it as e to the I times s of x minus q times the integral dx dot a, like such. In other words, this is nothing but e to the I, sorry, e to the minus iq integral over dx dot a times our original amplitude AI. Okay. I'm going to leave as an exercise for you to convince yourself that you can actually take that phase factor outside. We can take the line integral phase factor outside of the path integral. So the total amplitude is given by the superposition of these two amplitudes over the different paths, A1 and A2. So the total amplitude is computed as A, which is equal to A1 plus A2, which is then, A tilde is A tilde 1 plus A tilde 2, which is e to the, it's e to the minus I q integral over gamma 1 dx dot a a1 plus e to the minus I q integral over gamma 1 minus gamma 2, which is, we agreed, integral over the closed line integral, sorry, e to the minus iq closed line integral of dx dot a, like such, multiplying a2. And this in turn, I can write as e to the minus I q integral over gamma 1 dx dot a times a1 plus e to the minus I q times the magnetic flux through the plane, a2. Right. So this can be broken up into two parts. This first part is an overall factor, and this is irrelevant for our discussion anyway. This part, on the other hand, directly controls the interference, pattern that we'll see on the screen. So this factor controls the interference pattern. Okay, so that's the factor that we need to pay attention to. Now, note the following. If I change the magnetic flux in the region that is inaccessible to the particle, classically inaccessible to the particle, we can change the interference pattern in the same way that we discussed for the previous case, how the relative phase controls the shift of the interference pattern. So now, if I turn on the magnetic field by turning on a magnetic flux, I can change the interference pattern. So that's the first point to note. Point one, changing phi changes directly the interference pattern. Okay. Secondly, since the interference depends on the relative phase phi 1, 2, but only mod 2 pi, the shift in the pattern is also periodic. So if I change the magnetic flux, if I crank up the magnetic flux, I'll find a shift in the interference pattern, and that shift will be periodic. So point number two is that the interference pattern shift is periodic. And again, I can deduce this by basically just looking at the structure of the amplitudes. And then finally, and actually I don't need to make a note of this, this is just a look how clever we are statement. Finally, notice that we've actually managed to deduce all of this without actually doing a path integral on a non-simply connected space. Now, before I move on, I should tell you what I mean by this. So a space is called connected if I can reach any point in the space from another point in the space with a continuous path. So for example, if my space consists of the union of these two areas, then it is not connected because I have this gap in between. On the other hand, if I can reach any 2 points in the space by a continuous path that I can then deform into any other continuous path between those 2 points, then I say that my space is simply connected. So between these two, this is a non-connected path. So this is not connected. This is simply connected. And by this here, I mean this region here. And here, I'm talking about this interior region. So the shaded region is my space. And then finally, I have a region like the one we're currently talking about, which looks like this. Except we've excised a little area in there. And so the shaded region, which is our space of interest, is this region here, which I guess you'll see as soon as I lift my pen. And this region is called non-simply connected because even though I can join any 2 points that lie inside the shaded region by a continuous path, not all continuous paths can be deformed into each other. So for example, if I start off with a point here and a point there, I can join them up with a path that looks like this, or one that looks like this. And I can join them up with a path that looks like this. But I can't continuously deform the lower set of paths into the upper set of paths without cutting them, because I've got to go through this whole region. Okay, so this kind of space is called non-simply connected. Okay, and so technically, if we want to do this path integral, we've got to do the path integral on the correct configuration space. In other words, we've got to do the path integral on a non-simply connected space. Now, you certainly can do that. And the technique for doing that is to go to what's called the universal covering space of the non-simply connected space, which is the unique space that is simply connected, that projects down onto this non-simply connected space in an appropriate way. But doing path integrals on non-simply connected spaces is a non-trivial task, and not one that we need to grapple with if we want to try and understand the Aharonov-Bohm effect. So that's that was the key point here, and we managed to show this without actually doing the path integral on the non-simply connected space. Okay, so that's all I wanted to talk about today. Next time, we're going to continue this line of reasoning. In other words, we're going to continue doing these path integrals of this form, except now we're going to try and do something slightly different. We're going to try and build in particle statistics. I'm going to show you that fermions and bosons actually transform differently, and this is coded into the path integral. Not only that, we're going to discover that if we take the same line of reasoning that generally holds in any number of dimensions, and we focus on 2 spatial dimensions, then we're going to encounter a completely new set of objects that transform in a different way from bosons or fermions. These are called anions, and they exist in 2+1 dimensions. And these are actually, by one set of research programs, these are a great candidate for what would be a qubit or quantum bit that is used in quantum computing. So I'll say a little bit about that next time. Any questions?
No.
Great. Okay, so I will put this up on YouTube shortly, and then I'll see you next time.
Okay.